All right, let's go back. Let's get started and let's go back into the notes and what we were discussing last time. And particularly what we were talking about was deflection, okay? And one of the big points I want to get across is when we were doing moment capacity and shear capacity, those were strength considerations or safety considerations. When you calculate phi-mn or phi-vn or what have you, you're talking about the load that will cause this beam to fail, to literally crack, to not be able to resist load. That is not what we're talking about here. What we're talking about here is day-to-day use of the structure, just making sure that the structure meets its intended function. It's not a safety consideration. If a beam deflects too much, it does not mean that the beam is going to crack or fail or be unsafe to carry load. It's just not performing its intended function. Because of that, no load factors for serviceability. No 1.2 times the dead and 1.6 times the live. That's not what this is, okay? So we talked about what the difference is between strength and service limit states, and we're dealing with serviceability right now. And the main idea behind service limit states is because we're dealing in a world where we've got high strength materials and more economical ways to design. We can design fairly slender elements that can resist these load safety, but the problem is a member gets too slender, it deflects too much, and it's more than just safety that a structural engineer needs to provide. I mentioned on day one of this class, I mentioned a statement by an engineer by the name of Hardy Cross, and he said that strength was essential and otherwise unimportant. And what he was saying, in a larger sense, is that, of course you have to make sure that your structure is safe, but that's just one of a number of issues that you as a structural engineer are responsible for. You're responsible for the structure's constructability. It's day-to-day performance. It's not just strength. That's not the only issue. And there are many times where in the design of a structure, the safety isn't even the issue. It's the deflections or the vibration issues or the serviceability or the just elastic stress limits. That happens quite a bit. So it's something that needs to be addressed. Now, in terms of just computing deflections, you all should know how to do that. We did that last semester. So, direct integration, virtual work, conjugate beam method, we did that last semester. So you all should be good with that. The complicated issue with beams is the moment of inertia, the actual I value. Because if you look at a beam, let's say it's got a uniformly distributed load, some of those moments are probably going to exceed the cracking moment. And if that's the case, what you're going to find is some of that beam is going to be cracked and some of it isn't. So we don't use the gross moment of inertia. We don't use the cracked moment of inertia. We use an effective moment of inertia, which is somewhere in between. If you've got a 8,000 inches to the fourth gross moment of inertia and about a 4,000 cracked moment of inertia, the one you actually use for deflection is probably somewhere in between. And you compute that using the following expression. The big thing is your applied moment, no load factors. Okay? That's complication number one, but it's actually pretty simple. It's plug and chug. What really gets to be an issue is staged construction, because you can't just compute dead load deflection or live load deflection or each of these individual responses. You have to track the loads as they progress on the beam. Stage one, you take the beam, you set it on the supports. It's being subjected to only its dead load so you can compute that deflection. Then the building is subjected to its occupancy. You and I, the tables, the chairs, the computers, the desks, the file cabinets, the bookshelves, all of that. So in stage two, it is being subjected to its dead load and its live load at the same time. So you can't compute live load deflection, but you can compute dead load and then dead plus live and take the difference. Most of our deflection limits are based on the deflection that's generated by the building's occupancy, but buildings never truly see just the occupancy load. They see either the dead load or the dead load plus the live. So to actually compute live load deflection, you need to take the difference. Okay? Does that make sense? All right. Now, what we're going to do for this example is compute what is called instantaneous deflection. In other words, take the load, set it on the beam, how much does it deflect? Okay? It's pretty simple. What we're going to do after this is we're going to look at long-term deflections. Over time, the properties of concrete change. Concrete creeps. It undergoes shrinkage. It undergoes changes in humidity and temperature and what have you. Over time, properties of concrete change. So what we're going to do is look at immediate deflections and then long-term deflections. How do those deflections change over time? For now, just instantaneous deflection. So we've got a simply supported beam. It's got dead load. It's got live load. There's the beam. FC prime's 3 KSI, it's 60 KSI steel, although all we really need for this is just the modular ratio. And now we're going to compute live load deflection. All right. Sound good? All right. Now, let me go back to the example. Okay, so we go through, we listed the parameters, here's all the beam dimensions and what have you. We've got the gross moment of inertia, that was simple. It's a rectangle. It's just BH cubed over 12. And then the cracking moment. So the cracking moment, if you recall, I know it's been a while since we've done that, but we have. Remember, it's the modulus of rupture times the gross moment of inertia over y sub t. And then remember this, 7.5 square root of FC prime. So we've got the gross moment of inertia. We got the cracking moment. And then we spent last time, I think the rest of the time, looking at the transformed section, the cracked moment of inertia. So remember, this is probably bringing it back. This was like example 2 or 3 or something that we did in this class where we were looking at the cracked moment of inertia. Excuse me. So remember, you assume that all of the concrete in tension is ineffective. You take the area of steel and transform it into an effective lump of concrete by multiplying by n, the modular ratio. Remember, n's just your ratio of ES and the modulus of elasticity of your concrete. And then it's just that summing moments about the neutral axis. Went through and did all that, solved the quadratic, and then some parallel axis theorem to get the crack moment of inertia. And we stopped right here, I believe. All right, sound good? Okay, so what we're going to do is, keep in mind, we're going to compute the dead load deflection. Then we're going to compute the dead plus live and take the difference. Okay? So to start off with dead load deflection, what do we have? Well, we have our gross moment of inertia and our cracked moment of inertia. Again, makes sense that this is smaller because the section's cracked. It's not going to be as stiff. We've got our cracking moment of 27.39 foot kips, and our applied moment is 50. What's missing here? No load factors. This isn't 1.2 times the dead. We just take the raw loads as they are. Okay, so everybody okay with this? So just looking at the magnitudes of the moments, it makes sense that some of this beam is going to crack and some of it isn't. Like the maximum moment is 50, cracking moment's like 27.39, so our real moment of inertia or our effective moment of inertia is probably somewhere in between here. Sound good? Again, because load factoring, when you apply load factors, you're looking at the problem from a safety standpoint. You're asking how much load will cause this beam to literally fail, to fall down in the river. If grandma's on the concrete beam, you violate that load, grandma's going to fall. Okay? That's not what we're talking about here. What we're talking about here is the beam deflecting too much? That's not the same thing. Because we're not looking at this from a safety standpoint, we're not checking, we're not applying those load factors. That's a good question, and that's an important point to understand. Sound good? All right, any questions? Okay. So, we've got all of the ingredients necessary to compute our effective moment of inertia. We have these 2 moments of inertia and these 2 moments. So, can I go on to the next panel? All right, this is, I think it's like 14A. So our effective moment of inertia is the following expression. right? I didn't get that backwards. So the idea is you have, a portion of the moment of inertia times IG, or a portion of its IG and a portion of its I critical, and it's kind of like linear interpolation, not really, but somewhat. So cracked moment is 27.39 divided by 50. Remember that ratio is cubed, so when you calculate it, make sure you're taking that into account. And then that's times 8,000. What do we got? I'll make y'all do a little bit of work this morning. There we go. I had one, but no big deal. It's just rounding, whatnot. All right, so again, our moment of inertia isn't quite 8,000, and it's not 4,067. It's somewhere in between, because some of the beam's cracked and some of it isn't, okay? And that's how we compute what's effective. So to calculate the dead load deflection, all right, okay, to start off, let's look at our load. It's 1 kip per foot, which, because I want everything in consistent units for what I'm about to do, I'm going to say that that's 0.083 kips per inch. Everybody know how I did that? I took it and I divided it by 12, right? And then our length is, how long is the beam? Or 240 inches, right? Now, the big question is, if you have a beam that has a uniformly distributed load, how do you compute the deflection midspan? You don't need to remember the formula. I gave it to you. Didn't I, on day one? Oh, you've got to go back to your notes and look. Let me see this real quick. All right. Y'all remember this? All right, so tell me, what's the maximum deflection in a beam with a uniformly distributed load? You tell me. No, right now we're doing just the dead load. Then we're going to do the dead plus the live, and we're going to take the difference. There we go. All right. So, therefore, the deflection due to dead load is 5,384 EI. And our I is I effective. Y'all see that? Y'all see where we got that? Everybody see it? You got it? Everybody good? All right, okay. So we plug and chug. We've got 5 times 0.083 kips per inch times 240 inches, and that 240, not squared, raised to the fourth over 384. What's E? That's probably a good question. What is E? No. Now that would be if it was steel. This isn't a steel beam. It's a concrete beam. So what is E? We did it. We computed it in this problem. Say it again. There we go. 3122. Because it's E of the concrete. Remember, how do you compute that? It's 57,000 times the square root of FC prime. We did that. See, it's all coming together. All right, and then this is 4713.1 inches to the fourth. That's the thing with these deflection problems. They don't really become incredibly difficult, but it's all about bookkeeping. Make sure you're using the right E value, the right I value, the right load, stuff like that. It's not terribly complex. It's just the bookkeeping. So what do we got? There we go. I got something like, what the heck happened? I got this, 2, 4, 5, something like that. Okay. All right, so this beam under its dead load is going to deflect about 1/4 of an inch, okay? That's under the dead load. Now we're going to see what happens with the live load. All right, sound good? Am I good to move on? Okay, all right. Now, dead. The coffee hasn't kicked in. I'm going to blame the coffee. Okay. Now, we cannot do the live load directly, but what we can do is the dead plus the live. So a couple things. Let's make sure we're on the same page. So the moment of inertia, or the gross moment of inertia, and the cracked moment of inertia don't change. That's 8,000 inches to the fourth, and was it 4066.7? That doesn't change, okay? The cracked moment doesn't change as well. That's 27.39. What's our MA, though? It's not 50, okay? That's what changes. Our applied moment changes because now we've got more load. It's not just the dead load, it's the dead load plus the live load. So our MA is, again, WL squared over 8. It's still a simply supported beam uniformly distributed load, only it's we have to add that effect of the live load. Okay, now, again, what's missing? I'm not taking 1.2 times the dead and 1.6 times the live. It's not a factoring issue, okay? It's not a safety issue. We're not factoring the loads. So what was the live load, 0.7? Yeah, okay, so plug and chug, and that should give you excuse me, 85-foot kips. So now that we've got more moment, more of the beam's going to crack. So should our IE, our effective moment of inertia, is it going to be higher from the last part or lower? Help me. Before we even do any math, let's just think about this. If more of the beam has cracked, what's that going to do to the moment of inertia? It's going to get smaller, right? The beam is not as stiff because it's experiencing more load. Let's see if that happens. So our effective moment of inertia is the following. Fill it in. All right. Yes. Yeah. Where did you get the 1.2? I thought it was 1.0. I thought it's 1.0. Is it? What are you getting 1.2? You applying the load factors? Oh, okay. All right. What? What do we got here? There we go. Like about 41.98. Yeah. Now, what was this before? What was this on the last part? Like 47 something? So look what happened. More load on the beam, more of the beam has cracked, so this dropped. Make sense? All right. So now we can compute deflection. So our length is still 240 inches. Our dead load plus our live load is 1.7 kips per foot, which is 0.142 kips per inch. Okay? So how do we compute the deflection due to the dead load plus the live load? Well, (5WL to the fourth over 384 EI). Remember the moment of inertia of the concrete, the effective moment of inertia of the beam. So that's 0.142. And then that raised to the fourth. And then 384. We got 3122.02, and then 4198.3. What we got? Here we go. So, under the dead load, the beam deflected just shy of 1/4 of an inch. Under all of that load, it's deflecting 0.468. So how do we determine how much deflection was caused by just the live load? Subtract them. So, excuse me. You all have all this? Go ahead. Because if that's a great question, okay? You're talking about right here, okay? You can't do that. Well, because, okay, all right, the good question, all right, that's a good question. The reason why is because you won't be coupling this load and this moment of inertia properly. This moment of inertia corresponds to the total amount of load. Do you see what I mean? All right. If we were going along your path, then all we would do is, if we're going to do that, then we'd have to use just that much moment in this moment of inertia up here. But then we wouldn't be representing how much of the beam is truly cracked. Does that make sense? All right, think about it like this. If you're correct that we can just remove that and just use the live load, then we should be able to remove this and just look at the dead load. So we can compute dead load deflection, right? But would you get the same answer here as you did before? Your eye changes. You see what I mean? Really, the only way to do it is just to compute the dead load deflection, compute the whole deflection, and take the difference. It sucks, I know. See, in steel, it's not that complicated. In steel, the material properties don't change, so you don't have to go through all of this. So yeah. All right, has everybody got all this? All right. So, for live load deflection, it's pretty straightforward. So the deflection due to the dead load was 0.245, and the deflection due to the dead load plus the live load was 0.468. So how do we compute the live load deflection? We take the difference. And what is the live load deflection in this case? All right. Anybody have any questions? Sound good? All right. This is in your packet, right? This stuff? Okay, all right. So what we've done in this example, and I want to make sure everybody understands this, is we've computed the deflection from the live load instantaneously. So what I mean by that, just to be clear, we've computed the deflection solely due to the live load at the instant the live load is applied. Like, here's the live load, what's the deflection? Okay? There is a difference between how concrete beams respond, or how concrete responds instantaneously as opposed to over time. Over time, the properties of concrete, they change. Concrete undergoes material changes like creep, like shrinkage, like humidity. How many of y'all have had Huffman's materials classes? He talked about these things like creep and shrinkage. So you've heard this stuff. You know what I'm talking about. Okay. So over time, these properties change, and that's going to ultimately change the response of concrete beams under these loads. So now, one of the things that you'll find if you look at test data and you look at research on this over time, do you remember when we did doubly reinforced beams and we had steel on the bottom and steel up top? One of the things that you'll find is that over time, having compression steel, having that steel up top, remember I said there are a few benefits to having compression steel up top. One of those benefits is that it improves long-term deflection performance. This is what I'm talking about. Over time, those deflections will increase in a concrete beam. Having compression steel, that helps. Okay? So one of the other I guess you could say complicated notions that in the world of deflections for concrete is to ask how much of that load is a sustained. In other words, yeah, you might be designing that office building or that classroom for 80 pounds per square foot. Do you think that 80 pounds per square foot is going to be on that floor system all day, every day, all the time? Not necessarily the case. I mean, take the people in this room. In about 10 minutes, this class is going to be over and you all are going to be out of here, right? So this load on this floor system is not sustained. So in something like an office building, you might say, okay, 80 pounds per square foot, but really only 20% of that's going to be there all the time. Whereas, what if we're talking about something like a storage warehouse or a library, okay? If you look at something like like Sam's Club or something like that, you go to Sam's and you've got these big stacks and all these, heavy, pallets with Coke and 5-gallon jars of peanut butter and what have you. Well, that floor system is going to sustain that load all the time because it is seeing those heavy loads all day, every day. So a storage warehouse, you might see 100% of that design load sustained. Is there a hard and fast rule for if you're designing this building, take it to be 20%? If you're designing this building, take it to be 40%? No. This is just engineering judgment. You look at the system and what do you think makes sense, okay? So that's on you. You've got to use your judgment as to what value is appropriate. Does that make sense? Just depends on the project that you're working on, okay? Sound good? Now, how do we handle long-term deflections? Well, basically what we do is we treat it as simply as possible. We take immediate deflections and we adjust them by what we'll call a modification factor, this lambda value. And this lambda value is just what's inside the parentheses. So we take immediate deflections and we adjust them by the following parameter to get long-term deflections. Now, what is this parameter a function of? Well, first off, it's a function of rho prime. Rho prime is the reinforcement ratio for compression steel. So if you have steel in compression in your beam, you're going to get a benefit, okay? Now, how do you calculate that? Well, it's the area of steel divided by the effective area of the concrete, B times D, okay? If you have compression steel, you'll get a benefit. It's also a function of this time-dependent factor. How do you compute that? You look it up here. Now, this is a graph showing what your time-dependent factor is as a function of how long that load is sustained. To give you kind of an idea, for something like dead load, when we compute dead load deflections, we take those dead load deflections and we multiply them by 2 to account for that long-term effect. Why? Because dead loads are always there. They're always going to be there. Whereas for live loads, well, that's a function of how much of that load is sustained and how long it's going to be there. So this is the curve that represents it. Here's a few key values. So if it's on there for 3 months, our adjustment factor is 1. 6 months, it's about 1.2. 12 months here, it's about 1.4. 5 years or more. Anything else, you can interpolate it from the graph. What?
Never seen that before.
That's a Greek letter, that's xi.
Yeah, that's going to be a squiggle on my paper.
That's fine.
So heads up.
It's a Greek letter. I promise it's a Greek letter. So I'll just put a. Tell you what. Well, if you want, we can do this. We can call it. I don't know, like. Oh. We'll call it a smiley face. How's that? You can just put a smiley face. I swear it's a Greek letter. I promise. It's the lower xi. What? No, that's zeta. I was going to say, some of the fraternity people here were like, no, that's zeta. No, I promise it's real. Okay. Other. Am I wrong? All right. Does anybody have any questions other than the made-up symbol, the stuff I'm just making up? Well, it's usually in the uppercase format. It looks something like, I don't even have any markers. what is it? It's like that or something like that. The 3 lines. You know what I'm talking about? No. Okay. All right. That's the lowercase format. Like for instance, like if you've got omega, the lowercase is that. It's the lowercase. So.
On our next test, it's going to be like having the Greek alphabet or something.
You want me, oh, nah, lost my place. You want me to put that on the formula sheet, just the Greek alphabet?
Yeah, we can do that.
All right. Let me go back to what I was talking about before I was, forgetting the what. Man, I'm losing my train of thought here. We're talking about Greek letters. Okay, so let me sort of briefly lay out how you would fully assess long-term deflections in a beam. So you've got to compute a few different deflections, and I apologize, but once you get your cracked moment of inertia, your cracking moment, your gross moment of inertia, a lot of this is pretty tabularized. It's the same formulas over and over again. It's just a function of bookkeeping. So you'll compute your dead load deflection, your dead plus live, and your live load deflection, which is basically what we just did. You would do an additional calculation of what we call the dead plus sustained live loads. You'll say, okay, maybe 30% of those live loads are sustained over the design life. So you'll get your sustained live load deflection. And then in order to account for the total live load deflection, we'd say, all right, we calculate our immediate live load deflections, and then we ask, okay, well, how much dead load deflection is amplified by long-term effects, and then how much of that sustained live load is amplified by our duration. And plug and chug, it's pretty straightforward. So we'll look at this next time. We'll also look at deflection limits, which are usually a function of span length, like how much is this beam allowed to deflect. We'll then go back using our made-up symbols in this example we just did and ask ourselves, okay, we had a beam that had a dead load of 1 kip per foot, a live load of 0.7 kips per foot. Is it stiff enough to resist those deflections? And we'll be able to answer yes or no. Sound good? All right. What are we doing on Friday? All right. We're going to be back on Monday, ready and raring to go. All right.